Okay, welcome back for round two, or rather round one on a different fight. So we're going to change gears here a little bit and talk about this this magical thing called twistor theory. But I'll do my best from time to time to try to convince you that there's a reason to have this discussion alongside a discussion about celestial holography. Okay, so I don't have a reading list for these lectures, mainly because lots of the foundational papers don't have archive numbers. They're old papers, actual papers. But I'll from time to time maybe point out when I think, oh, this is a good reference, people should look at this paper or something like that. Okay, so let's just remind ourselves a little bit of the setting we're going to be playing in. So let's take blackboard bold M. This is going to be what I call complexified Minkowski space. So don't let those words fool you and make you think it's something complicated. This is just C4 with a holomorphic metric. Okay, so it's just Minkowski space, but I let the coordinates take on complex values, and holomorphic because I don't put bars over everything. Okay, so when I write blackboard bold M, I mean I'm thinking of this complexified Minkowski space and real Minkowski space. Jiminy cricket, okay. So Lorentzian real Minkowski space R13, this sits inside complexified Minkowski space as the obvious real slice, right? I just let my x0, x1, x2, x3 take on real values, and then this complexified metric descends to the real Minkowski metric. Now, you may say, okay, Tim, why do this? For the same reason that I relaxed myself about reality conditions in the previous lecture. Okay, we're just going to let ourselves talk about things in this complexified setting, and if we need a reality condition, we'll impose it. And I'll try to be kind of clear about that. So, yeah, there are no X-bar components here. Yeah, that's what I mean by a holomorphic metric. Good, yeah. Recall from last lecture that we can replace these four kind of, if you like, vectorial or coordinates on complexified Minkowski space with two-spinner coordinates. So this is x alpha alpha dot, 1 divided by root 2, x naught plus x3, x1 minus I, x2, x1 plus I, x2, x naught minus x3. So we can use these things as coordinates on M, in which case our metric written in this two-spinner formalism is epsilon alpha beta, epsilon alpha dot beta dot, dx alpha alpha dot, dx beta beta dot. So I'm just reminding us of what we learned an alarmingly short time ago. Okay, so you might ask that, okay, Lorentzian real Minkowski space set inside the complexified Minkowski space in this completely obvious way in the sort of usual coordinates. What about in these two-spinner coordinates? because this matrix has some i's floating around in it, so it's not just going to be as easy as saying that this matrix is a real valued 2 by 2 matrix, because that obviously won't give us Lorentzian real Minkowski space. So R13 here corresponds to this 2 by 2 matrix X alpha alpha dot being Hermitian. Okay, and that's a nice exercise you can work through for yourself. Check that if this is indeed the case, it forces x naught, x1, x2, and x3 to be real valued, and really does give you the R13 real slice inside of complexified Minkowski space. But we learned something from this, which I only kind of alluded to in the previous lecture. I mean, this Hermitian conjugation involves complex conjugation and a transpose. So that means it switches the two SL2 spinor representations, right? So with this, if you like, reality structure, if I have some kappa alpha AB, so some two-component undotted spinor, complex conjugation sends this thing to a dotted spinor whose components are A bar, B bar, where bar just represents the usual notion of complex conjugation. And similarly, kappa twiddle alpha dot, if this thing has component CD, then this gets sent to some kappa twiddle bar alpha, C bar, D bar. And this explains why the reality condition we got for our null vectors before was that kappa twiddle had to be the complex conjugate of kappa, right? Because this Hermitian reality condition means that the two SL2 representations are interchanged. Okay. So, okay, this is all just somehow setting the stage. So now we talked a lot in the last lecture about CP1 as the Riemann sphere and how we could describe this in terms of homogeneous coordinates. So now we can think of a higher dimensional complex projective space, the three-dimensional complex projective space. So this is defined in abstract terms as the space of all lines complex lines through the origin in C4, right? But just like with CP1, there's a kind of nice intuitive hands-on definition, which is just in terms of homogeneous coordinates. This can be constructed using homogeneous coordinates. So what these are four complex numbers. I'm going to call them big ZA, Z1, Z2, Z3, Z4, which are not all simultaneously 0, so they're not all allowed to be 0 at once, and I consider them equivalent up to overall scalings by a non-vanishing complex number. So this is just exactly what we did with our Z alphas before in the previous lecture. We've just pumped up the dimension, okay? So just like Z alpha with two components modulo this projective scale described a one complex dimensional space, these four complex numbers, Z1, Z2, Z3, Z4, modulo this projective scale define a three-dimensional complex space, right? That's why we call this thing CP3, okay? So here, you know, before when we were talking about the sphere, the affine patches were just two copies of the complex plane. One of them that covered everything but the North Pole, the other one covered everything but the South Pole. So now there are four patches. So So the affine patches, I can give them some label, ui, and this is just the set where the ith homogeneous coordinate is non-vanishing. From I going from 1 to 4. If it's not vanishing, I can pull it out, right? And then that's just a projective rescaling. So on, say, for example, on U1, we have the affine coordinate. So here I could have ZA is equal to big Z1, 1, big Z2 over big Z, sorry, big Z2 over big Z1, big Z3 over big Z1, big Z4 over big Z1. And then these three complex numbers would be the three affine coordinates on that patch. That's how you see that this is a three-dimensional complex space. So on each of these affine patches, you only get three complex numbers. Okay? So this is CP3. Most of us hopefully have met this, this idea of projective space before at some point. So now, we're going to decompose these four complex numbers into two-component Weyl spinners of SL2. So we're going to say ZA, this is four complex numbers. Two of them I'm going to call mu alpha dot, and two of them I'm going to call lambda alpha. Okay? I haven't done anything sophisticated here. I've just given fancy names to these four complex numbers. And remember, we consider these things only up to overall projective rescalings. Okay. So the reason for doing this decomposition is it now gives us, allows us to write down a linear relationship, a linear but non-local relationship between points in CP3 and points in complexified Minkowski space. So this is a linear holomorphic algebraic relation between CP3 and M. So what is this? It's just going to be mu alpha dot is equal to I x alpha alpha dot lambda alpha. So x labels a point in complexified Minkowski space, and mu and lambda label a point in CP3. They're the components of a homogeneous coordinate for a point in CP3. Okay? Now, there's this funny factor of I that I've put here. This doesn't have to be there. It makes some formulae look nicer. It makes some formulae look uglier. I will forget about this factor of I sporadically throughout these lectures. If you get worried that there should be an I somewhere, tell me. Almost certainly there should be, and I've just forgotten to write it, okay? So what are these? What is the actual geometric content of this simple linear equation? All right, so fix, let's start by fix some point x in our complexified Minkowski space. So if we forget about projective scaling for a second. So what do I mean by projective scale? I mean this equivalence up to overall scaling by a non-vanishing complex number. For now, let's just forget about this. And then, if I wrote this equation, you wouldn't have to think twice. You'd tell me exactly what it meant. For fixed x, this is an equation defining a linearly holomorphically embedded plane, a copy of C2 inside of C4, right? So if I forget about complex scale, these ZAs are just, or sorry, if I forget about projective scale, the ZAs are just coordinates, holomorphic coordinates on C4, and this is a linear relation for two linear equations. So this is defining a plane, just a C2 inside of C4, right? So then to get the projective scale back in the game, we just need to kind of quotient out by projective scale on each side. So if I have C2 and I quotient out by projective scale, that gets me down to CP1, just like it did in the last lecture. If I have C4 and I quotient by projective scale, that gets me down to CP3. So a point in complexified Minkowski space gives a linear holomorphically embedded Riemann sphere in CP3. So that's one direction of what you should think of that algebraic equation is telling you. Fix a point in complexified Minkowski space, I get an extended object in this CP3. That's the sense in which this relation is non-local. It doesn't send a point to a point, it sends a point to a sphere. And when I say the sphere is linearly embedded, I just mean that those are linear equations. When I say it's holomorphically embedded, I mean there's no bars anywhere. Right? It's a holomorphic equation. Okay? And an upshot of that is that when we think about these spheres that we're getting in CP3, you can imagine them just as lines in R3. Right? So all of your geometric intuition from your day-to-day life is going to carry over to these things. And you might say, well, why is that the case? If I have two spheres, they could intersect like in a circle or something, right? And lines can't do that. But if my two spheres intersect in a circle, I have to define that circle using Z and Z bar, right? That's not something holomorphic. So holomorphic Riemann spheres can only intersect in points, right? Just like lines can only intersect in points. Okay. So really, if you're having trouble picturing something I'm thinking about, just think about lines in R3, and somehow the intuition is going to be good enough most of the time. Okay, so that's one kind of direction, but what about the other way around? What does a point in CP3 define in complexified Minkowski space under these equations? So conversely, let's fix some Z, some point Z in three-dimensional complex projective space. Now, based on what I literally just said about these holomorphic Riemann spheres, I can always define such a point by the intersection of two of these, if you like, holomorphic lines, right? So you can always realize Z as the intersection of two of these lines. Let me call them big X and big Y. So I will call the linearly holomorphically embedded Riemann sphere corresponding to a point X in complexified Minkowski space. I will call that corresponding Riemann sphere big X inside of CP3. So this big X, this is topologically a P1 inside CP3. Okay? So any point in CP3, I can always cook up two of these lines that intersect in that point. Let me call them X and Y. Okay? So that means that I have mu alpha dot is equal to I X alpha alpha dot lambda alpha, and mu alpha dot is equal to I Y alpha alpha dot lambda alpha, where X and Y are the points in complexified Minkowski space corresponding to these two lines. Okay? So then I can subtract one of these equations from the other. Right? That means that I X minus Y alpha alpha dot is, lambda alpha is equal to 0. I haven't done anything sophisticated here. I've just taken my two algebraic equations and I've subtracted one from the other. Let me remind you what this expression is actually equal to. This is equal to I epsilon alpha beta X minus Y beta alpha dot lambda alpha. And we're saying that that's equal to 0. So remember, we always contract spinor indices via the Levi-Civitas symbol. It's the unique SL2 invariant tensor that we have in the game. So if I have a quantity, X minus Y beta alpha dot, and I contract it with the Levi-Civitas symbol against lambda and I get 0, there's only two options, right? In 2 dimensions, there's only 2 options. Either X minus Y is equal to 0, or X minus Y has to be proportional to lambda. There are no other options, right? Because epsilon alpha beta, this is the unique up to scale skew symmetric object we have to play with in 2 dimensions. Okay, so this implies that X minus Y alpha alpha dot has to be proportional to lambda. Another way of saying is I have to be able to write it as lambda alpha lambda twiddle alpha dot for some lambda twiddle, right? That's what I get when I take this equation and I subtract this equation from it. So these are the same mu's, right? Because they're intersecting at a unique point Z. Does it answer your question? Okay, cool. Okay? So now the light bulb goes off because this is a null vector, right? Okay. So we learn one thing really easily, which is that if I have 2 of these lines in CP3 and they intersect in a point, that immediately implies that the 2 points, the 2 corresponding points in complexified Minkowski space have to be null separated. Right? This is an if and only if statement. Right? Because if these things are null separate, it means I can write them in this way, and that means their incidence relations have to obey this. I call this thing in the box, we'll call this equation an incidence relation from time to time when I forget to call it something else. Okay? So we learned that these lines in CP3 intersect if and only if their corresponding points in complexified Minkowski spacetime are null separated. But we also learned that any point in CP3 defined a family of these null vectors, right? Because this didn't fix lambda twiddle alpha dot. Any lambda twiddle alpha dot would do. So the upshot here is the following. So the first upshot was that 2 of these lines in CP3 intersect if and only if the corresponding little x, little y in M are null separated. But the other upshot is that Z3 defines a family of null vectors which all have the form lambda alpha, lambda twiddle alpha dot. So lambda alpha is fixed. It's determined by Z, fixed up to a scale. It's determined by Z. Lambda twiddle is up for grabs. Any lambda twiddle will do in terms of this kind of algebraic calculation that we did up there. So this, right, if I have a family of these null vectors, how many of them, how big is this family? Well, there's two components in lambda twiddle alpha dot, right? So I have a two-dimensional family of these null vectors. This defines a totally null two-plane in complexified Minkowski space, which we'll call alpha sub Z. So totally null means that every tangent vector to this two-plane has this form. And I label it with a Z to remind us that the null vectors, their undotted bit is all proportional to lambda, the bit of the point up in CP3 that we started with, okay? So this correspondence is very non-local in both directions. A point in complexified Minkowski space gives us a sphere up in CP3, and a point up in CP3 gives us this whole totally null two-plane inside of complexified Minkowski space. Yes?
Probably not a relevant question, but in complexified Minkowski space, is there a physical interpretation to null separated form?
Yeah, so okay, this is a good question. So you might worry that because we're in a complexified space-time, what does it mean for a vector to have some kind of signature associated with it? And it's true that there's no longer any meaning for the kind of sign of the norm of the vector, but having a null norm is still meaningful. And from a physical perspective, I'm not so sure what one should say, other than if you, for instance, so let me make a comment here that I'll make without proof, but we can talk about the proof later if you want. You could ask what happened if I took the R13, the Lorentzian real Minkowski space inside of the complexified one, and then what would happen is this totally null two-plane would intersect the real slice in a line. That line would be precisely where this lambda twiddle is lambda bar, right? And that's a real null vector. So if you like, this totally null two-plane contains one real null vector that is associated with the intersection of that null plane with the real slice. This isn't a good answer to your question, but it's an answer. Okay. So, what are they? Yep, okay. Following on from this comment, actually, it's a reasonable place to observe that nothing about what I've said so far has really used the Minkowski metric per se. So what we have used is this idea of null vectors, right? But the concept of a null vector is something that's conformally invariant, right? Null cones, if you conformally rescale your space-time, null cones don't do anything. They stay the same. So this whole construction, this correspondence between CP3 and complexified Minkowski space has been completely conformally invariant so far. So this correspondence has been conformally invariant. That's, if you like, because it only knows about null structures. Okay. So if we really want to kind of say that this thing is happening for a complexified Minkowski space and not any complexified conformally flat metric, then we need to somehow know about the boundary conditions of Minkowski space. But to do that, we can observe that not all points in CP3 play nicely with this construction. So what do I mean by this? Consider the following set. I'm going to call it I. This is going to be the set of all homogeneous coordinates in CP3, all these ZAs, where the last two homogeneous coordinates, lambda alpha, are both simultaneously 0. Now, this I, this is a linear equation. It's a holomorphic equation, and there are two of them. And it's also scale invariant, because 0 times any non-vanishing complex number is 0. So this is also a line. This is also an example of one of our linearly, holomorphically embedded CP1s, but clearly it's not on the same footing as the ones that are defined kind of generically with this incidence relation we wrote down. And in fact, the incidence relations remember, these are these mu alpha dot is equal to I x alpha alpha dot lambda alpha. If both lambdas are 0, right, and x is any finite point in complexified Minkowski space, this forces, so if I restrict this to the this line I that I've just defined, this forces, both components of mu alpha dot to vanish, right? But now we're in trouble, right? Because homogeneous coordinates are not all allowed to vanish simultaneously. It's one of their defining features. So actually, if we force this incidence relation to try and describe this line in CP3, we get a contradiction. This is no good. Right? So somehow our correspondence between complexified Minkowski space and CP3 doesn't actually hold on all of CP3. There's this special line which falls outside of its regime of validity because it can't be described using homogeneous coordinates. Okay? So what we're going to do is we're going to cut this line out of CP3. And that's what we're going to call Twistor space. So this is all the Zs in CP3 such that the lambdas are not allowed to vanish simultaneously. Okay? So I've taken CP3, I've removed one CP1 from it. This one. So if you like, this is CP3 set minus this line I. So what I'm left with is an open subset of CP3. Okay? And this is what we're going to call Twistor space. And I'm not going to show this in detail because, well, it's not ugly, it's beautiful, but it's going to take me further afield from what I would like to say, but it can be shown that if you conformally compactify complexified Minkowski space to some conformal compactification M bar, then this line that we've removed from CP3 corresponds precisely to the point at spatial infinity in that conformal compactification. So this is the sense in which removing this line I breaks the conformal invariance of the construction. If I tell you about where infinity is, I've told you what the conformal factor of the metric is, right? So this Twistor space, by removing this line I, it knows that the space of lines that are described by the incidence relations here, this really is complexified Minkowski space, not any conformally flat space-time. Okay? But you're going to have to take my word for it on this point for now. So, if you like, we can do some kind of summary. On one side, we have Twistor space. On the other side, we have complexified Minkowski space-time. And we can take a point in here, and that gives us one of these lines, which I'll now call Twistor lines, which are holomorphically linearly embedded CP1s in PT. And if I take a point Z in PT, then this is going to give me one of these totally null two planes alpha sub Z inside of complexified Minkowski space. Okay? So far you might say, okay, this has been some like nice geometry. Does it bias anything? All I've told you so far is there's some nice kind of geometric way to re-encode the geometry of complexified Minkowski space. You can get real Minkowski space out of this by imposing appropriate reality conditions on everything. But you know, what does it buy you? And that's the next thing I'd like to try and.
Sorry, can I ask?
Yeah, please.
I'm a bit worried about this choice that we made. We split it according to before, to mu and lambda.
Mm-hmm.
In the beginning, they was at equal footing, and it was kind of okay. But right now, we choose that lambda have some condition, and they are like really separated.
Yeah, absolutely.
It should correspond to something in the process.
It does. It does. So this splitting corresponds to choosing a point at infinity in Minkowski space. So before I did that, I didn't know what infinity was or what it looked like, and that was the statement that I hadn't fixed a conformal structure. So now, disentangling mu and lambda, if you like, tells me that I really am in Minkowski space and not in complexified ADS or something. So yeah, it absolutely breaks, if you like, the symmetry between mu. I mean, there isn't a, but it breaks the fact that mu and lambda are kind of on an equal footing. But that's important because we needed it to distinguish Minkowski space from any other conformally flat space-time. Does it answer your question? Okay, cool. Yeah. Okay, so okie dokie. So now we're going to take a little detour just to set up an interesting physical problem that this correspondence helps us solve. And I'll be precise about what I mean by solving in a minute. So we're going to talk about something called zero rest mass fields. Or ZRMs, as I will repeatedly abbreviate them. Okay? So we're going to consider totally symmetric spinor fields which either have all undotted or all dotted spinors. And by totally symmetric, I mean they're totally symmetric in these two spinor indices. Or they could have no spinor indices, in which case they'd just be a scalar, phi. And we're going to ask that these things are conformal densities of weight minus 1. That's just a fancy word for how they transform under a conformal rescaling. So if epsilon alpha beta goes to some omega epsilon alpha beta, and epsilon alpha dot beta dot goes to some same omega epsilon alpha dot beta dot. That's the same as my Minkowski metric a to ab going to omega squared a to ab. It's just a conformal transformation, right? Then phi alpha 1 to alpha 2s goes to phi inverse. And similarly for the dotted one. Okay? So that's all I mean by conformal density of weight minus 1. So we say that such fields are zero rest mass fields on M if they obey the following PDEs. So if I have one of these symmetric conformal weight minus 1 spinor fields with no dotted indices, I take one partial derivative and I contract on the undotted spinor indices and I set that equal to 0. If it's the other chirality, I just do the same thing but on the dotted indices. And if it's spin 0, I just take the wave operator. So obviously, spin 0, 0 rest mass field, this is just code for free massless scalar, right, on Minkowski space. But these things are something a little more gnarly looking. And just as an aside, you can show that these 0 rest mass equations are conformally invariant. So what do I mean by this? I mean, let's take the kind of negative helicity example with all undotted spinor indices. If I have some phi that solves this equation in Minkowski space, and then I do a conformal rescaling with conformal factor omega, then the conformal rescaled phi solves the equation in the new conformal frame. Okay? That's what I mean by them being conformally invariant. Obviously, there's a little subtlety with the wave equation. This thing goes to the conformally invariant wave equation, so it's like box plus r over 12. Yeah. For a Dirac field? Okay, so in some sense I'm going to answer your question in a minute, but let me try to answer it straight away. With fields like this, you could only build a massless Dirac field. Yeah. So somehow these are only going to give you like Weyl neutrinos, not an honest. So, I'm really sorry. Can you repeat? Majorana fields. Only massless is the thing. This construction will only capture massless free fields. Yeah. So somehow anything that's more sophisticated than a Weyl spinor, if it's in this framework, it will actually just break apart into separate Weyl spinors of different chiralities. Yeah. No, good question. Okay, so okay, we all like this equation. We spent more or less the whole of the last lecture talking about solutions of this equation, but I claim that actually we also care about these equations. If you haven't seen them before, I'm going to try to convince you that secretly you have. You just might not have realized it. Okay, so let's talk about ZRMs and free fields. So the claim is that solutions of the zero rest mass equations are in one-to-one correspondence with solutions of the usual massless free field equations on M, okay? So the idea is going to be that rather than thinking about, for instance, a metric perturbation that satisfies the linearized Einstein equation, we could somehow think of some zero rest mass field where this S is 2, so some totally symmetric four-component spinner that obeys this first order PDE, okay? So everything I'm going to say for like the next 10 minutes or something is going to be to try to convince you of this fact. So recall our helicity basis for gravitons, let's say in momentum eigenstate basis. There we had some HAB, which could have helicity plus or minus, some perturbations, some linear perturbation to the Minkowski metric. And we wrote this thing in terms of plus or minus helicity polarization tensor e to the I p dot x. Let me just fix outgoing boundary conditions for now to save myself having to write minus plus everywhere. So that's just fixing the plus sign in the argument of that exponential. So, and I'll remind you that for p alpha alpha dot equals omega z alpha z bar alpha dot, this was our favorite parameterization of a null momentum from the last vector, or the last lecture. We could write these polarization vectors, for instance, like z alpha, z beta, iota bar alpha dot, iota bar beta dot. Okay, so I'm just writing the same formulae that we wrote in the previous lecture, just to remind you. So now let's consider the kind of gauge invariant information that corresponds to these metric perturbations, right? Or gauge covariant information. So the metric is like a gauge field. The gauge invariant information is in its linearized Riemann tensor, right? That's like the linearized field strength of a graviton. Okay, so what does the linearized Riemann tensor of metric perturbations like that look like? Well, to answer that, let's first consider the Riemann tensor R, A, B, C, D of some metric G. Doesn't need to be linear now. I give you a metric, a holomorphic metric. So this is some complexified metric on C4, and I compute its curvature tensor. Now, for each one of these indices, A, B, C, D, I get a pair of SL2 spinor indices, right? Just through this usual yoga of contracting with Pauli matrices, right? But without doing any calculations at all, I know that that two-spinor representation of this R can be decomposed into certain SL2 irreducibles, just because this tensor has some symmetries, right? So just using algebraic properties, of the Riemann tensor, I know we can decompose R alpha alpha dot, beta beta dot, gamma gamma dot, delta delta dot into a bunch of SL2 irreducibles which have the following form. Sorry, everyone should see this once, so just bear with me. Okay. So again, there's no kind of calculation that's happened here. If you like, you can view this as some big Young tableau manipulation with SL2, okay? So just using the algebraic symmetries of the Riemann tensor, you can decompose the thing into these SL2 irreducibles where these things psi twiddle and psi are totally symmetric. Okay? And then you can mess around with this a bit. Again, you don't need to do any hard calculation. Because these things are totally symmetric, if I start taking traces of the Riemann tensor, it means I'm going to be coming through with some epsilons and epsilon dots upstairs, and anytime those hook into these guys, I'm going to get 0, right? Because they're totally symmetric and epsilon is skew, right? So these things are the trace-free bits of the Riemann curvature tensor, also known as the Weil tensor. Right? Okay. And, fun exercise, count the degrees of freedom in a rank 4 totally symmetric two-component spinner. Count the degrees of freedom in the Weil tensor. You'll get the same numbers. Good? Absolutely, absolutely. So these things were the Weil curvature, phi, alpha, beta, gamma dot, delta dot. This corresponds to trace-free Ricci curvature, and then the Ricci scalar is the, okay, where this 12 came from, that did require some calculation to know that whatever scalar coefficient of all these epsilons, I actually wanted it to match what I would call the Ricci scalar in the usual sense.
Here we see that R is in some sense, Ricci scalar is in some sense independent. So we divided Riemann curvature, psi bar, phi bar,
Yeah.
which are independent.
Exactly, exactly. So because this is the trace-free bit of the Ricci curvature, it's like you've trace subtracted all the trace bit is out this kind of back term, if you like. Yeah, very good. And R is the, yeah. This is the Ricci scalar. Okay, so no dynamical statement has been made here. This has just been an exercise in representation theory. Okay, and this is, again, a nonlinear statement. Take your favorite metric. You can in 4 dimensions, you can always decompose the Riemann tensor of that metric in terms of these kind of two-spinner irreducibles. Okay? But now that means that we can take these linear metric perturbations, compute their curvature, their linearized Riemann curvature tensor, and read off the associated irreducibles. Okay? So for instance, we could take R, A, B, C, D of our negative helicity graviton wave function. And what you get, if you compute the Riemann tensor of this, you only get one term, this one, right? So that means that H minus AB, has vanishing linearized Ricci scalar, vanishing linearized trace-free Ricci tensor, and it only has this irreducible bit of the Weil tensor, this bit 0, right? So that implies that H minus AB only has the kind of linearized psi alpha beta gamma curvature sitting in it. Good. So this thing is not conformally invariant, but it's a conformal density of weight minus 1. The Weil tensor being conformally invariant depends on whether the indices are. Right? If I raise an index, that gets rid of that minus 1. So good catch. With all the indices down, it's weight minus 1.
But there are no Ricci scale or Ricci curvature.
No.
Because we asked this to be
Exactly. The whole, where we got this from was solving the linearized vacuum Einstein equation. So if we'd computed this and we'd found a phi, we did something wrong back before we started messing with the two-spinner formalism. Right? So the fact that the phi and r reps of this guy are 0 is a consistency check that we solved the vacuum Einstein equations. And then the fact that only psi and not psi twiddle comes is just a statement that it's a helicity eigenstate. So somehow for massless fields, helicity is the same as self-duality. So in a sense that I'll explain another day, you should think of this as the kind of self-dual part of the Weil tensor, and this is the anti-self-dual part of the Weil tensor. And the negative helicity guy only has anti-self-dual Weil curvature. Similarly, do the same calculation for H plus. What do you know? You only get the self-dual rep. Okay? And now we see that, lo and behold, each of these things satisfies the relevant zero rest mass equation. If I take the psi alpha beta gamma delta corresponding to H minus, that's just this thing. I hit it with one partial derivative with respect to x and contract on the undotted index, I get 0. Why do I get 0? The derivative brings down a p. P is like omega z, z bar. And then I contract on z. Z goes with z, that's 0. Right? Same thing happens for the positive helicity guy. Okay? So these things are zero rest mass fields. Okay? And in fact, we can say something even a bit more general. So what we've shown is that the things we call graviton wave functions correspond to zero rest mass fields of spin 2. This is kind of one direction, but in fact, zero rest mass fields of spin 2 always correspond to linearized metric perturbations that solve the vacuum Einstein equations. So it's an if and only if statement. So how do we see this? So if, for instance, you had some metric that obeyed that the tilde, the twiddled irrep of the Weil tensor was 0, and its Ricci tensor vanished, so it was a vacuum solution of the Einstein equations, then the differential Bianchi identity for the Riemann tensor reduces to nabla alpha alpha dot psi alpha beta gamma delta equals 0. This is a nonlinear statement. If I linearize it, what it's saying is that if I have a graviton perturbation that solves the vacuum Einstein equations and is and whose tilde Weil tensor vanishes, then the only remaining irreducible satisfies the zero rest mass equations. And it's just a Bianchi identity. So in other words, it's saying that the zero rest mass equations are just Bianchi identities for your totally symmetric spinner to have come from a gauge field that solved the equation of motion you wanted to solve in the first place. So the upshot is that these ZRM equations are just Bianchi identities. Ensuring that the zero rest mass field came from a free field in the usual sense that we would think about it. So for spin 2, the fact that these equations hold is just, if you like, a consistency check telling you that this psi alpha beta gamma delta came about as the Weyl tensor, the linearized Weyl tensor, of a linear metric perturbation that solved the vacuum Einstein equations and was negative helicity. Okay? So this is the sense in which these zero rest mass equations are the massless free field equations. They're just the free field equations written for the field strengths, right, in the two-spinner formalism. Okay? All right, so now back to twistor theory. So we're now going to talk about something called the Penrose transform. And let me somehow give you the punchline before I tell you the story. The punchline is that twistor theory generates all solutions to this set of PDEs that we call the zero rest mass equations. And now the rest of the story is to tell you in what sense it generates these solutions. Okay. So for this, to tell you this story, I need to do a bit of terminology unpacking. I'll be as rough as possible about this. I don't want anyone to get bogged down in it, but let's let curly O of K this is something called the sheaf of locally holomorphic functions on twistor space, homogeneous of weight K, where K is some integer. Okay, so those sound like fancy words, but what it means is something extremely concrete. Sections of this sheaf are just functions of z and z bar on twistor space, so I can think of them as functions of the homogeneous coordinates on twistor space, such that if I rescale z by r, z bar by r bar, I get r to the k f of z. Z bar for all non-vanishing complex numbers r. Okay? So you see curly O of k, this is what you think immediately. You're just thinking functions that are kind of locally holomorphic, so that's what I mean when I say you don't see any powers of r bar getting kicked out here. Of weight k, just means it scales like weight k with respect to r. Okay? Okay, so next bit of terminology, we're going to call 0, 1 forms on twistor space. Those 1 forms which only point in an anti-holomorphic direction. What do I mean by this? I mean these are some F's which look like F A bar D Z bar of A bar, written in terms of the homogeneous coordinates. And we say that we'll denote the space of these things by omega 0, 1 of PT. So if I write this, you think 1 forms whose 1 form leg points in a bar direction, it's an anti-holomorphic direction, living on twistor space. Okay. No, I haven't told you anything about, these coefficients are functions that depend on Z and Z bar. Okay. So then we can tie this notion and that notion together and start talking about 0, 1 forms on twistor space that have a certain weight under projective rescaling, right? So let omega 0, 1 PT OK be 1 forms on 0, 1 forms on twistor space, so 1 forms whose form component points in an anti-holomorphic direction such that F R Z R bar Z bar is R to K Z bar. Okay? So you would read this as a mathematician as the space of all 0, 1 forms on twistor space taking values in this sheaf O of K, but you should just think of it in these super concrete terms, right? 0, 1 forms that scale in a certain way, that have a certain homogeneity. Okay, so now we're going to say that a 0, 1 form on twistor space of weight K is holomorphic if it satisfies the Cauchy-Riemann equations. So if d bar of F is 0, where d bar is the anti-holomorphic Dolbeau operator. Okay, so this thing sins PQ forms to PQ plus 1 forms. Right? I just take an anti-holomorphic derivative in an anti-holomorphic direction. That's what the thing's doing. And then this acts via wedge product, right? So if this is acting on some differential form, I wedge this dz bar against everything else. Okay? So if I have a 0, 1 form and it's annihilated by d bar, I say that it's holomorphic. In the same way that if I had a function on C that was annihilated by d bar, I'd say it was holomorphic because it obeyed the Cauchy-Riemann equations. Okay? So note that this operator, del bar, d bar, is nilpotent. So why is it nilpotent? It's nilpotent for the same reason that the exterior derivative is nilpotent, right? Because if I act with this thing twice, I'm going to get 2 dz bars wedged against each other, but those are going to be contracted into 2 partial derivatives, and partial derivatives commute. Okay? So this operator is nilpotent, and so if there exists some function on twistor space of weight K, G, such that I can write my 0, 1 form as d bar of that function, it immediately follows that this 0, 1 form will be holomorphic, right? Right? Because d bar squares to 0. Right? So this is a very cheap way of cooking up holomorphic 0, 1 forms, and it makes sense to develop some kind of notion of non-trivial holomorphic 0, 1 forms. 0, 1 forms that are d bar closed, but not d bar exact. And that's precisely this notion of cohomology, okay, which some of us may already be familiar with. So this is something called a Dolbeau cohomology group. We're going to call H01 PT okay. This is going to be the set of all 0, 1 forms on Twistor space of weight k such that d bar of those 1 forms is 0 modulo the set of all 0, 1 forms on Twistor space of weight k such that that 1 form could be written as d bar of a function. Okay? So when I write H01 PT OK, this is just fancy symbols for this super concrete thing. It's holomorphic 0, 1 forms of weight k on Twistor space where we mod out, we count as 0 any of those holomorphic 1 forms which we got cheaply by just taking d bar of a function. Okay? And here it's worth pointing out, although I won't prove it, that you might worry that, well, okay, I haven't told you why you should care about this group, but maybe this group is empty. Maybe Twistor space doesn't have any interesting 0, 1 forms. There was a kind of question about this in Simone's lecture earlier about kind of applicability of the Poincare lemma. If you had some function that was closed, he assumed that that implied there existed something you could write, 1 form that was closed, it implied the existence of a function that you could take d of it to give you that 1 form, right? So all of those things would be 0 in this cohomology group. So the existence of interesting cohomology is somehow tied to the existence of kind of interesting topology. And if, instead of PT, we took here CP3, the whole of CP3, these would be empty. But because we removed that line, we now have this open subset, and it has interesting topology. And these cohomology groups are not empty. Okay, so we just built some tool case where the big hammer in the toolkit was this cohomology, this Dolbeau cohomology group. So why the heck did we do this? We have the following theorem. This is, in some sense, due to Penrose in the 70s, but I think it would be fair to say that the mathematical proof of it was established later in the 80s. Eastwood, Penrose, and Wells. So what is the theorem? The theorem is that the set of all 0 rest mass fields of helicity H on complexified Minkowski space is in 1-to-1 correspondence with the cohomology group H01 on PT curly O 2H minus 2. Okay? So this is a really gnarly statement. Here you have some set of PDEs, and it's saying that you can solve all of these PDEs in terms of some analytic data on some projective variety. That's pretty cool. So this H is the helicity of the field, so it runs over the integer and half integers, positive and negative. And it's basically saying if you want to cook up a field of helicity H, you just cook up a non-trivial holomorphic one form on Twistor space of the appropriate weight. Okay? So the proof is not easy. Okay, so that means that I won't tell you about it, basically. So one direction is very easy, and we'll write that down in a second. That's if you give me an H01, it's very easy to cook up the corresponding zero rest mass field. What's much harder to show is that all zero rest mass fields arise in this way. Now, of course, if we have any honest card-carrying mathematicians in the room, they know that this word all doesn't exist in pure mathematics, right? There's some suitable qualifications one needs to put in front of it. So here there's some assumptions about regularity, but these are pretty mild assumptions. So really, from a physics point of view, you should think of it as all zero rest mass fields. So the direction where you show that all zero rest mass fields on M arise from cohomology in Twistor space, this requires some homological algebra, which is fancy terminology for you write lots of commutative diagrams, and then you do something to these commutative diagrams. They start out very big, they get smaller and smaller, and at the end of the day, you get an isomorphism, right? So, so if you want, I'm making this sound like it's kind of not enlightening at all, which is not true. But if you want to learn the story, read this paper. I think this is 1980, 1981 maybe, Com Math Phys. It's the only paper that this set of people wrote together, so it's easy to find on Spires. And in some sense, they build it from the ground up, so you don't need to know anything. You don't need to know, you don't need to read Galfa and Grav or whatever to understand it. You just get going, and they'll show you the light if you stick with it for long enough. But let's think about it the other way around. So let's take some F in this cohomology group, 2H minus 2, and then let F restricted to X just denote the pullback of this 0, 1 form to the line in Twistor space corresponding to the point X in complexified Minkowski space, right? Remember, we established a point in complexified Minkowski space corresponds to one of these Twistor lines, so I can restrict my 0, 1 form to that line, and all that means is that I just evaluate it on the incidence relations, right? So this is just, I evaluate it on mu alpha dot is equal to I X alpha alpha dot lambda alpha. So when I write F restrict X, that's what I mean, okay, in practical terms. Okay, so now I can define the zero rest mass field from this data in the following way. So if I have negative helicity, that's alpha 1 up to alpha 2 absolute value of H of X. I take the integral over the Twistor line corresponding to the point X. And then I'll define what I mean by my notation here in a moment. Where this big D lambda, this is just shorthand for lambda, D lambda, which remember is just lambda alpha, D lambda alpha. If I have positive helicity, I take the integral over X, D lambda, and then I take a bunch of derivatives with respect to mu. Restrict the whole thing to X. And if I have a scalar, then I just integral it over the line, D lambda, wedge F, restrict X. Okay, fun exercise. Convince yourself that these integrals make sense mathematically. So let's look at the scalar one for fun, right? So for this integral to make sense, right, the integrand has to be a 1, 1 form, so a top form that I can actually integrate over CP1, and it has to be weightless, right, so that it's projectively well-defined. So d lambda, this is proportional to d actual exterior d lambda, so this is a 1, 0 form. It's a differential form that points in the holomorphic direction, and it's weight 2, right, because I have 2 powers of lambda here. So this is weight plus 2, 1, 0 form. F, for a scalar, I set h equal to 0, right, so this is weight minus 2. So the weight minus 2 of this F eats the weight plus 2 of d lambda, so it's projectively well-defined. And F was a 0, 1 form on Twistor space. The pullback to the Twistor line is holomorphic because the incidence relations are holomorphic. So if it was a 0, 1 form on Twistor space, F restrict x is a 0, 1 form on this line, x, right? So I have a 1, 1 form of weight 0. So this integral is well-defined. And you could do the same counting for the other cases as well. Okay? And then it's easy to show that these fields, these spinor fields that we've defined by means of these integral formulae automatically obey the zero rest mass equations. And that's just a consequence of the holomorphy of the one forms representatives on Twistor space. So, for instance, okay, so it's easy to show that these obey the ZRMs. For instance, let's take the negative helicity case. So d alpha alpha dot 1, say phi alpha 1, phi alpha 2h. So I can bring this derivative inside of that integral using the incidence relations. So I have an integral over x, d lambda wedge, lambda alpha 1, lambda alpha 2, absolute value of h. And then I have lambda alpha 1 d by d mu alpha dot. But then I also have to have the anti-holomorphic one. And that's all acting on f and restricted to x, right? So the second term is 0 because f was holomorphic, and this is an anti-holomorphic derivative. And then the first term is 0 because I have lambda contracted into lambda. That contraction is skew symmetric, so it's 0. Okay? So it's just the holomorphy of the Twistor representative, the fact that it was in H01, so it's annihilated by d bar. And then the rest of it just follows algebraically. So you can check this for the other two cases of the scalar. And the positive helicity field to amuse yourself, if you like. Okay, but the thing I'd like to end with is like, okay, how do you actually use this in principle, right? So we spent the first lecture on celestial holography talking about cooking up, how to, if we're doing scattering amplitudes, we need explicit solutions of these zero rest mass equations to plug in as the external states in our scattering process. And so if this theorem is true, it means I should be able to write down a cohomology class on Twistor space that corresponds to a momentum eigenstate. And also a cohomology class on Twistor space that corresponds to a conformal primary wave function. That's what the theorem is telling us. Okay. So I'd just like to convince you that you can actually do this. So, example, let's do positive helicity graviton momentum eigenstate. So first, there's a little nifty tool. First, let's define something I'll call delta bar of z. So here z, sorry, not to be confused with our homogeneous coordinate on PT. Z is just a complex number. this thing I'm going to define to be 1 over 2 pi I dz bar d by dz bar 1 over z, or if you like, 1 over 2 pi I d bar 1 over z for all z in C. Okay, so you might say, well, this is 0, right? Because z is holomorphic and d bar is an anti-holomorphic derivative. And it is holomorphic almost everywhere, except when z is equal to 0, when it blows up. And then this thing acts like a delta function. And so one way of seeing this is, so this is what we might call a holomorphic delta function. To see why, let's let D be some bounded domain in C containing the origin. And we'll let gamma be the boundary of this domain. And let F be holomorphic function on D. Well, then I can consider integrating dz delta bar of z times f over d, right? And if this thing really is supposed to be like a delta function, I'd better get f evaluated at the origin when I do this integral. So just using my definition, this is 1 over 2 pi I, integral over d, dz, d bar, 1 over z, f of z. And I've just used my definition from up there. But because f is holomorphic, I can bring it inside that d bar and nothing happens. Right? So this whole thing is actually a total derivative, 1 over 2 pi I, integral over d, d bar, dz, f of z over z. Right? So then Stokes' theorem tells me that that's just a contour integral around the boundary, 1 over 2 pi I, contour around gamma, dz, f of z over z. And then Cauchy's theorem tells me that that's just f at 0. So that's the sense in which this notation is justified, calling this thing a holomorphic delta function. Okay? This is a fairly incomplete blackboard. We'll just use this. Okay, so now I'm going to write down a 0-1 form on Twistor space. So consider H to be iota lambda cubed over iota z cubed. I'm going to put a 1 over omega squared there. Delta bar, angle bracket, lambda z. And then I'm going to have an exp of omega mu z bar iota z over iota. Nope. Yeah. Okay. So my claim is that this is an object that lives in H01 on PT in curly O2. Right? So let's check the weight first. Right? So I have 3 powers of lambda here. Then I have this delta bar of the angle bracket between lambda and z. But this goes like 1 over its argument. Right? So this prefactor here is actually weight 2 in lambda. Right? And then the argument of the exponential is weightless on Twistor space. I have a mu upstairs and a lambda downstairs. So this thing lives in curly O2. Okay, it's also a 0-1 form because of this delta bar. Right? So delta bar isn't just a function, it has this exterior derivative piece, and it points in an anti-holomorphic direction. Right? So this thing is a 0, some sort of 0-1 object on Twistor space, and my claim is that it's closed. So why is it closed? If I hit this thing with d bar, you might worry it looks like there's an essential singularity hanging out in this exponential, right? But that d bar is only going to see the bit of the essential singularity that's coordinatized by lambda. Right? But we already have a differential form in lambda here. So d bar h, this would be proportional, if you like, to d lambda bar, wedge d lambda bar, and this is 0 on Twistor space precisely because we've removed the bit of Twistor space where all the lambdas are allowed to be independent, so they are allowed to be 0 simultaneously. That means there's only one degree of freedom in lambda. So this thing is d bar closed. And then you can show that if you take this thing and you throw it into that integral formula, you get precisely the zero rest mass field of the positive helicity momentum eigenstate graviton. Okay, so this is just a kind of one demonstration of this Penrose transform in action, but we can use this nowadays to do all sorts of gnarly stuff, like compute scattering amplitudes from Twistor space. Okay, but I think I've tested everyone's patience for long enough. Yeah, see everyone tomorrow, I guess.